All my life I have been trying to find new problems to work on, or in some abstract sense a better problem, than what you're working on right now. And so I started off with this low temperature spectroscopy in Bell Labs. At the time it was or at least to say we thought it was the best place in the free world to do physical science research. I began to read the literature on how you generate interesting chemical reactions, and I found this literature on colloidal semiconductors. Colloid is a suspension of small particles in a liquid, and if you put dust in water, you'll have a scattering liquid, or milk. Milk is a colloid, large particles. If the particles are small enough, the colloid becomes clear. It doesn't scatter in the same way that milk does, but it has a color that's the color of the colloidal particles. After a couple of years, I stumbled into this fact to the observation that the band gap of a semiconductor particle experimentally was a function of size. And that was a curiosity to begin with, but it eventually took over all of my research. Late 1982, when we first made this discovery, and I didn't know what it meant in the beginning. When you sat at the desk and thought about it, it was a first-class research problem in the sense that it was very interesting basic research that was relevant to the industry, for sure. And so we saw this effect, and we had to try and find ways to make smaller and smaller particles. You start with a solvent, that's the liquid, and you want to create a reaction in the solvent that grows particles. So you can inject reagents, and you want to nucleate and grow a solid phase, and if you let this chemical reaction run indefinitely, you'll get big particles. They'll fall to the bottom of the beaker. And so for the purposes of making and studying very small quantum dots, what we wanted to do was start this reaction to make a solid particle, but stop the reaction as soon as we could, just at the point of nucleation, when there might be 100 or 1,000 atoms in the particle, and then stop it right there and somehow study it. So you can see the band gap is basically directly related to the diameter. The smaller the particle, the higher is the energy of the band gap. So small semiconductor particles absorb light in the blue, and intermediate sized particles absorb light in the green, and larger ones in the red. So this quantum mechanical effect shifts the threshold all the way across the visible, from the red to the green to the blue to the ultraviolet. The straightforward application was that it would affect the design of transistors as the transistor naturally got smaller and smaller, because the scientific principles that I would discover would have to be incorporated into the design properties of the transistor, because the fundamental properties of the silicon or the transistor material were changing. Conductivity, band gap size, all of these parameters which go into the electrical engineering of transistors would change. So I understood that. But the actual application of the particles themselves outside of that context, we had no idea. Really no idea. For example, the first application of these particles in any significant way has been in biological imaging, to replace dye molecules directly. And that only came about 10 years after I first started working on this. So there's sort of two things that people are interested in. One is to maximize the light emission from the particles, to just use them as dye molecules, or particles for converting one color light into another color light. And many applications are going down this road right now. The other thing that people are interested in is the photovoltaic application, where you create the electron-hole pair, but then you separate the charge. The electron has to jump off the particle, and the hole has to jump off the particle and go in the other direction, and you'll flow current in an external circuit. I have to say, truthfully, I am surprised. On the one hand, we understood that the science was important, but I never had any good sense that the particles themselves would be important industrially. We thought that they might somehow be, one quantum dot might be used in the transistor design. That's never played out, basically, and the industry has gone in a different direction. And it's like most things in science. It takes one of the truisms in science is that the basic research scientists who invent something are not the best judges of where it's useful.